Today's discussion covers a recent paper titled Modulation-Based Field Theory, a Unified Approach to Fundamental Physical Laws, authored by Christopher Young. The paper proposes a novel mathematical framework designed to unify fundamental physics across scales, from quantum particles up to cosmological structures, without relying on parameter fine-tuning. It aims to integrate quantum mechanics, gravity, and field theory into a coherent, modulation-based field structure, addressing long-standing challenges such as the black hole information paradox and the quantum measurement problem. The introduction sets the stage by emphasizing the persistent difficulty in physics. While individual domains like quantum mechanics and general relativity have been remarkably successful, a fully unified description that works seamlessly across all scales remains elusive. Previous unification attempts focused either on force interactions or geometric quantum gravity, often requiring extra assumptions or parameters. In contrast, this approach treats fundamental interactions and emergent complex systems as manifestations of a single underlying oscillatory field structure. Importantly, fundamental constants, such as the gravitational constant and the fine structure constant, are not externally imposed, but emerge naturally from the internal structure of the theory. This represents a departure from conventional models like the Standard Model, which require careful calibration of such constants. The core mathematical object introduced is the generalization-based field equation. It extends traditional Lagrangian field theory by introducing a modulation parameter that governs interactions across different physical domains. While it shares superficial similarities with path integral formulations from Feynman, this equation includes additional terms that enable natural unification of quantum mechanics and gravity, overcoming incompatibilities present in earlier approaches. The integral form of the equation ensures conservation laws rooted in Noether's theorem are maintained, while extending conservation principles to new modulation symmetries, enriching the theoretical framework. The approach conceptually parallels holographic principles in string theory, but achieves unification through a distinct mathematical architecture that preserves standard space-time dimensionality, augmented by modulation dynamics. Within this framework, the fundamental energy field is described by the field variable, representing all forces and particles. Particle states correspond to excitations of this field, providing a unified quantum framework that naturally includes both fermions and bosons through symmetry breaking. Unlike the Copenhagen interpretation, which treats measurement as an additional postulate, or many worlds, which multiplies ontological entities, this approach models quantum superposition and measurement as intrinsic aspects of the field's modulation behavior. It shares conceptual ground with Bohm's pilot wave theory in offering a deterministic underpinning, but differs by deriving quantum behavior directly from interactions between field components and modulation terms, eliminating the need for separate guiding equations. Quantum phenomena such as superposition and entanglement emerge naturally from field properties, providing a more intuitive conceptual foundation than many conventional interpretations. Spin is incorporated through interaction terms involving weighted sinusoidal modulations, unifying spin-half fermions and spin-1 bosons within the same field modulation framework. This contrasts with traditional quantum field theory, where different spin states require distinct mathematical treatments. The universal weighting functions ensure spin states arise as fixed structured oscillations, extending naturally to higher spin states. Statistical behaviors also emerge from resonance structures, surpassing previous approaches that treated spin as fundamental without deeper explanation. Charge dynamics are governed by a potential term that unifies electromagnetic interactions with quantum behavior. Charge conservation arises from inherent field symmetries, aligning with Noether's theorem, while charge itself emerges as a property of the structured field modulation rather than a fundamental attribute. This unified treatment connects charge with other field properties, removing the need for independent postulates. The temporal energy term governs the field's evolution over time and controls wave propagation across scales, linking quantum state evolution to energy conservation without additional postulates. It harmonizes quantum time evolution with relativistic spacetime, resolving traditional tensions between these frameworks. The spatial energy term captures field gradients and spatial variation, unifying quantum and classical behaviors and influencing particle localization without requiring wave function collapse postulates. It also integrates smoothly with curved spacetime treatments, enabling consistent gravitational modeling without separate mathematical structures. The potential energy term incorporates multiple physical influences, deriving gravitational, electromagnetic, strong nuclear, and weak nuclear forces from the unified field structure. Gravitational potential emerges naturally from field geometry, while nuclear forces arise from symmetry breaking and field symmetries, providing conceptual and mathematical unification of all fundamental forces. Auxiliary modulation coordinates extend standard spacetime geometry, offering new perspectives on dark energy and quantum vacuum effects. Quantum vacuum fluctuations are modeled as structured modulation fluctuations, providing deterministic explanations for non-local quantum correlations and entanglement via modulation geometry. This approach offers a causal deterministic explanation for phenomena traditionally considered acausal or requiring faster-than-light influences, preserving locality in a deeper sense. Field interactions emerge naturally without requiring renormalization. Vacuum polarization and virtual particle effects arise from deterministic oscillatory structures weighted by universal resonance profiles. The weighting functions eliminate the need for iterative adjustments and external constraints common in conventional quantum field theory, ensuring mathematical stability and self-regulation. Vacuum energy is interpreted as arising from structured fluctuations rather than stochastic randomness, removing the need for artificial cutoffs and counterterms. A key mathematical innovation is the incorporation of a universal resonance weighting function, which replaces dynamic modulation terms with fixed, pre-computed oscillations. This deterministic weighting governs fundamental interactions, ensuring that coupling strengths and force behaviors arise intrinsically rather than through empirical tuning. The weighting function's pre-computed values for the first 5 harmonics provide structured resonance conditions that underpin all interaction strengths, linking particle masses, coupling constants, and force carrier properties through harmonic and phase relationships. The framework extends to black hole physics by modifying classical gravitational metrics with modulation-based weighting functions. This approach preserves gravitational curvature while incorporating higher dimensional effects, resolving classical singularities by demonstrating finite curvature at the center and preserving information through higher dimensional channels. It naturally incorporates quantum effects near black holes, smoothing transitions between quantum and classical regimes, and resolving the black hole information paradox. The event horizon structure is modified to include quantum effects and mechanisms for information storage, with modulation coupling generating non-local correlations. Hawking radiation is systematically modified through dimensional interference, offering new insights into black hole thermodynamics and information preservation consistent with both quantum theory and general relativity. The results section presents detailed derivations showing how fundamental constants emerge naturally from the framework's structured oscillatory behavior combined with the universal weighting functions. The gravitational constant G arises from the potential energy term and field curvature, with its value derived precisely from vacuum field structure and modulation dynamics rather than treated as an empirical parameter. Calculations reproduce the experimentally measured value of G to high precision without external input. Similarly, the fine structure constant A emerges from oscillatory coupling terms governing photon-electron interactions. Its value is derived from field modulation terms, matching experimental measurements with extraordinary precision without reliance on complex quantum electrodynamics calculations. Planck's constant E is derived from the temporal energy term controlling quantized energy oscillations, emerging as a resonance outcome of field oscillations rather than an imposed parameter, again matching known values precisely. The speed of light c follows from balancing spatial and temporal variations in the field, interpreted as the resonance propagation speed of vacuum oscillations. This derivation provides a deeper explanation for the universal speed limit than the postulated invariance in special relativity. The elementary charge E is derived from the interaction between charge and vector potentials within the field, emerging as a structured oscillation amplitude consistent with the defined SI value. Beyond constants, the framework reduces to well-known physical equations under appropriate limits, demonstrating its unifying power. Newton's law of universal gravitation emerges naturally from the potential term under static conditions. Einstein's field equations extend with modulation weighting functions, providing dynamic gravitational coupling and a smooth transition between quantum and classical gravitational regimes. The Schrödinger equation arises as the non-relativistic limit, focusing on temporal and spatial energy terms, with the complex phase factor emerging naturally from modulation geometry. Maxwell's equations are recovered from the oscillatory terms governing electromagnetic interactions, with electric and magnetic fields defined by scalar and vector potentials derived from the field. Coupling constants such as permittivity and permeability emerge naturally from weighting functions. The Dirac equation for spin 1/2 particles arises from modulation interactions and spatial derivatives, providing a physical interpretation of the Dirac matrices and mass terms from field dynamics. The Klein-Gordon equation for spin 0 relativistic particles appears from second-order temporal and spatial derivatives combined with rest mass contributions. Planck's law for blackbody radiation emerges from the quantized oscillatory field modes, providing a more fundamental explanation for energy quantization in thermal radiation. Lorentz transformations result from the invariance of the field equation under coordinate changes, deriving special relativity's mathematical foundation from modulation geometry rather than postulated invariance. Coulomb's law arises from static charge interactions in the potential term, with permittivity constants determined by the weighting functions. The Born rule for quantum probabilities emerges from oscillatory field intensities, providing an underlying physical basis for quantum measurement probabilities. The Navier-Stokes equations for fluid dynamics are derived from collective field excitations, connecting quantum field behavior with macroscopic fluid phenomena. The Friedmann equations governing cosmological expansion follow from the potential energy term applied to homogeneous isotropic universes, linking quantum-scale field dynamics with large-scale cosmology. The quantum harmonic oscillator's energy levels appear directly from oscillatory terms, including zero-point energy as a natural consequence of modulation structure. Thermodynamic laws emerge from energy conservation and information flow in the field, connecting entropy increase and energy exchange to modulation dynamics. The de Broglie wavelength relation arises from wave-particle duality embedded in field oscillations, clarifying the origin of wavelength-momentum correspondence. The Heisenberg uncertainty principle is derived as a mathematical consequence of complementary modulation properties in position and momentum space, offering a physical understanding of quantum indeterminacy. Noether's theorem, linking symmetries to conservation laws, emerges from the integral formulation of the field equation, producing conservation of energy, momentum, and angular momentum as natural consequences. Lagrangian mechanics and the principle of least action arise from energy terms in the field, connecting classical mechanics to field theory and quantum mechanics within a single framework. Black hole thermodynamics, including the Bekenstein-Hawking entropy formula, is derived from modulation-enhanced gravitational metrics, resolving the information paradox by preserving information through structured modulation channels. Finally, Euler's rotation equations for rigid body dynamics are recovered from rotational field excitations, unifying quantum spin and classical rotation. In summary, this comprehensive set of reductions demonstrates how 20 fundamental physical equations and principles emerge as special cases of the generalized modulation-based field equation. This unification spans classical and quantum mechanics, electromagnetism, thermodynamics, relativity, fluid dynamics, and cosmology, providing a mathematically elegant and conceptually coherent framework. The discussion highlights the significance of deriving fundamental constants and physical laws from deeper mathematical principles without arbitrary parameters or fine-tuning. This contrasts with anthropic or multiverse explanations and offers a more parsimonious explanation for the precise values observed in nature. The framework's smooth reduction to established theories and its avoidance of radical departures or unobservable dimensions strengthen its theoretical credibility. Importantly, the paper outlines testable predictions that diverge from conventional theories, including modifications to black hole entropy, specific high-energy particle interaction patterns, and gravitational wave signatures detectable by next-generation observatories. These predictions provide avenues for experimental validation and potential falsification. By providing a mathematically rigorous, empirically connected, and conceptually unified approach, the structured oscillatory field theory proposes a paradigm shift in how fundamental physical phenomena are understood, unifying disparate domains under a common modulation-based mathematical structure. This aligns with historical analyses of scientific revolutions, where new conceptual frameworks enable breakthroughs beyond incremental data accumulation. In conclusion, the paper offers a detailed mathematical model that unifies fundamental physics through modulation-based field dynamics, naturally deriving constants, known physical laws, and resolving long-standing theoretical challenges. Its implications span quantum mechanics, gravity, thermodynamics, and cosmology, providing a fertile ground for further theoretical development and experimental testing.